Welcome everyone. So in today's session we'll be studying about analog and mixed mode VLSI design. This is a 3 credit syllabus. So that means to say number of lecture hours is 3 per week and the total contact hours is 39 hours. So as per the syllabus goes, there are 5 units. The first one is Introduction to Analog Design. Why analog, why integrated circuits, why CMOS, general concepts, level of abstraction, robust analog design, basic MOS devices, general consideration, MOS IV characteristics, second order effect and MOS device models. And in the first unit itself we have one more chapter, that is data converter fundamentals, and this will be from textbook 1 as well as from textbook 2. So this is total contact hours is 9 hours. And the second unit is data converter architecture, that includes DAC architecture, digital input code, resistor string, R2 to R ladder network, etc. Third unit is ADC architecture. ADC architecture will be flash, two-step flash architecture, two-step flash ADC, pipeline ADC, integrating ADC and successive approximation ADC. Fourth one is current source and sink, and fifth one is single stage amplifiers. So the textbook will also be Neil West is the textbook, and so today we will be starting with the first unit. So the first unit, first topic is why analog. So why analog is nothing but what do you mean by. First we'll come to know, we'll go through what is an analog signal. So what is an analog signal? What is the difference between an analog signal and a digital signal? So an analog signal is nothing but analog input, or analog signal is nothing but the waveforms. Okay, the waveforms which we give, which is an analog input. So that will be connected to digital, that will be converted into digital format by zeros and ones. How? There are several different techniques to convert from an analog signal to a digital signal. One smallest example is, or simplest example is sampling. Okay, so when you sample the analog signal, so the discrete waveform will be obtained and the analog signal will be converted into a digital signal. Okay, so that is why analog means sometimes there will be possibilities, or there are possibilities where the input given to the computer or a device is analog in nature. Analog inputs are nothing but the physical inputs which are given by a human or an environment. Okay, for example, if you go for a temperature sensor, it is an analog input. The temperature is because it is measured through environment, so that has to be converted into a digital format. So that will be done in your second unit and third unit. Okay, this chapter and this chapter, where analog versus digital conversion and digital versus analog conversion will happen. So whenever you give an input to a computer, that is when you are typing or when you use a mouse, so that is an analog input. That analog input is converted into zeros and ones by a converter, that is analog to digital converter, that is ADC converter. ADC, okay, convert, C stands for converter, ADC. Similar, and once it is converted, the entire the computer actually processes the unit, processes the information given in the analog format, and it will be and the output will be provided. The output provided will be again in the digital format, but your output should be in analog format, because your screens, everything you have to see, that is a person has to see. Okay, so for those things, what happens, the digital output which we obtain after the processing of the digital input will be converted into an analog output. So that is where the digital to analog converter happened. Now analog to digital converter will happen. Okay, so these things will be going through in your upcoming chapters. Okay, now what are levels of abstractions? There are different kinds of levels of abstraction. Why integrated? Next topic is, first one is why analog, second is why integrated. What do you mean by integrated? Integrated means integrating or incorporating number of other components into one. Okay, so for example, if you take your computer, it has a processor, motherboard, RAM, ROM, screen. So everything is a different part, and each part is integrated together to obtain one particular unit. Okay, that is your computer. So that is why integration is very much important. So when you integrate things, it will be much simpler, and the device will become much the device will be reduced in size. Okay, that is why integration is very much important. Next, why CMOS? Why CMOS? You guys already know why CMOS, because CMOS has a very good it can be used as an on-off switch, and it is very good in it gives you very good resistance, and mainly it can be used as a complementary MOS structures. Okay, next, general concepts, that is level of abstraction, robust analog design. Levels of abstractions are nothing but there are different kinds of abstractions. So abstraction is nothing but levels. Okay, like how Bloom's taxonomy level is there, L1, L2, L3. Similarly, levels of abstraction in a circuit. So first will be, if you go for an NOT circuit, okay, if you go for a NOT circuit, first one will be what? First level of abstraction. Okay, so this will be the NOT circuit. Okay, second level of abstraction, so this will be a NOT circuit. Correct? Input, output. Third level of abstraction will be architecture. This is symbol level, this is circuit level. Okay, symbol, circuit, architecture level. Architecture level means the architecture of this NOT will be there. Next, forces integrated integrated level, where many such NOT gates will be there, and one this NOT gate will also be there. So these are the levels of abstractions. Okay, so these are all general concepts which are there for you guys to understand. That's all. Then after this will be robust analog design. So what do you mean by robust analog design? Whenever you're doing a design, so the design has to be robust. Robust is nothing but sturdy, and it has to be capable of working under any kind of conditions. Okay, working under any kind of conditions, and it should be susceptible for any kind of damage which can occur due to either temperature or due to environmental factors. So that is why whenever you are designing an circuit, it has to be robust. Okay, no matter it is an analog circuit or a digital circuit. So that is what it is. Now let's come to your important part, that is basic MOS device physics. So this is your first unit, which is basic MOS device physics. Okay, so this nothing but the general topics here. So from here it starts. Now general consideration, MOSFET as a switch. So I told you why we use MOSFET, right? So we use MOSFET as a switch. So we know why it is, because you have studied in your VLSI also why it acts as a switch. Because why? Anyways, we'll go through it. Before delving into the actual operation of the MOSFET, we consider a simplistic model of the device so as to gain a feeling for what the transistor is expected to be and which aspects of its behavior are important. So this is figure 1 shows you the symbol of an N-type MOSFET revealing 3 terminals, that is gate, source and drain. The later two are interchangeable because the device is symmetric. Okay, when operating as a switch, the transistor connects the source and the drain together in the gate voltage, that is VG. Source and the drain together. You guys have gone through, you guys have studied in VLSI that there will be no channel which will be formed. So this will be the gate, source and drain, gate, source and drain. So there will be no channel which will be formed here. So as and when VGS is increased and when it reaches the threshold voltage, so slowly a channel will be created between the source and the drain. So the electrons in the source will be traveled from source to drain, and then the conduction will occur. So that is why it is used as a switch. Okay, so that is what is explained here. Okay, next this is the MOSFET structure. So as you can see, this is an cross section of a MOSFET. So here you can see source is there. First is substrate is a P substrate because it is an NMOS. For PMOS it is N substrate, and NMOS will be here. Okay, n regions where p it's a reverse. So if there's a p substrate, n region will be here. If it's an n substrate, p region will be here. Okay, so the substrate is a p type substrate, so where diffusion occurs, and you guys know about the fabrication process in your FCMOS, where the fabrication occurs, and due to the diffusion region, the n diffusion process, the n region will be formed here and n region will be formed here. So the gate will be formed by placing layers of other materials on it. So source, gate and drain will be here. So next, source and gate, whenever it is made, say as you can see, L effective and L drawn. So L effective is the length of the channel, which is effective channel. So this is what the length has to increase, that the channel length has to increase in for the case to conduct between the source and the drain. Okay, so this is a basic structure of a MOS. Here you can see L effective is equal to L drawn minus 2LD. Okay, this is for the substrate connection. So substrate connection, when you were drawing the this one, so 1 second, when you were drawing the MOS device, so first we are drawing it like this: gate, source and drain. So the source, so this will be like this, the source will be connected to the substrate here. This is the substrate. So rather than connect, this is a P, this is N, this is N, this is P substrate. So rather than connecting from here to here, we can connect here only where there is place and where the substrate is P. So that is what it is shown here. Okay, that is the substrate connection. So this is again different substrate connections, how we can write, and this is PMOS inside an N well. So as you can see, this is a twin tub process which happens, so which you have studied in your CMOS. Now this is the general symbols of a MOS, that is NMOS is written like this, PMOS is written like this. You can see the change in the arrow mark also. Wherever the source is there, the arrow mark will be placed near the source, and for the NMOS, the arrow mark will be moving outside. For PMOS, the arrow mark will be moving inside. Okay. Next, we will come to the important topic, that is MOS IV characteristics. In this section, we analyze the generation and transport of charge in MOSFET as a function of terminal voltage. Our objective is to derive equation for the IV characteristics such that we can evaluate our abstraction from device physics level to circuit level. Okay, so first is threshold voltage. It was there in your previous FCMOS also, the threshold voltage. I'll just go through what is the threshold voltage. Threshold voltage is nothing but the voltage above which the device starts to conduct. So 0.7 volts is the threshold voltage for the MOSFET, where above which the MOSFET will start to conduct. Okay, so if you can see this is a P substrate. When there is a P substrate, this is an NMOS device. NMOS is there, and when VG is made, when the current is passed through, when the gate voltage is made more positive, what happens is the ions, negative ions, will start accumulating near the region between the source and the drain here, between the source and the drain. Okay, so when this happens, the region below the gate acts like a capacitor. This is a depletion capacitor, and this is oxide capacitor, COX. You guys have studied in your scaling, right? So when it is made more positive, what happens is electrons will start, these are the negative ions, electrons will start forming at the region below the gate. So when there is an electron which has formed below the region of the gate, the electrons pushes the holes down, and it fills up the place below the gate between the source and the drain. Okay, so that is how the conduction will happen. Okay, so you have to write this equation, that is VTH, this one. This is the threshold equation, that is VTH equals 5ms plus 2 plus Q depletion by COX. Okay, this is your VTH equation. So this you have to write it down. Now I'll just tell you what are the terms there. QMS is the difference between work function of a polysilicon gate and the silicon substrate, which you have to write. 5F is nothing but KT by Q natural log of n sub by ni. Q is the electron charge, n sub is the doping concentration of the substrate, Q dep is the charge in the depletion region, and COX is the gate oxide per unit area. So if they ask you about this IV characteristics, that is V threshold, first you have to write this V threshold equation, write those diagrams and explain each terms of the V threshold region. Okay, so from we'll see now what are the components which are here, this one, this one, this one, this one. So first is Q dep. Q dep is given by square root of 4Q ESI by 5F by N sub. Okay, where ESI denotes the dielectric constant of the silicon. Since COX appears very frequently in the device and circuit calculation, it is helpful to remember that TOX equals 50 amperes and COX is 6.9. Okay, that you have to write. In practice, the native threshold value obtained from the above equation may not be suited for circuit design, that is VTH is 0, and the device does not turn on for VG is greater than 0. For this reason, the threshold voltage is typically adjusted by how it is adjusted, 0.7 only, okay, by implementation of dopants into the channel area during device fabrication, in essence altering the doping level of the substrate. Okay, so how the threshold region is increased? The threshold region is increased by adding the dopant during the fabrication process. Okay, so that is how the threshold is increased for a MOSFET. So I hope you understood this. Again, inversion region appears. So when VG is when VG is reverse biased, what happens is, and electrons which were formed there will be converted. Okay, the turn on phenomena in a PMOS device, this is similar to that of NFET, but all of the polarities will be reversed. So that was for N type semiconductor, this is for P type semiconductor. Okay, now this is the main derivation of an IV characteristics. Okay, first you consider this, draw this. Okay, first consider a semiconductor bar carrying current I. Okay, this is a semiconductor bar which is carrying a current I. If the charge density, that is Q, charge density along the direction of the current is QD, coulombs per meter, and the velocity of the charge is V meters per second. Okay, so then I is given by what? Charge density by velocity. Okay, so consider this as an semiconductor bar which is carrying a current I. So what is the movement of the current depends on? Movement of the current will depend on the velocity of the electrons and the charge density which is placed on in the charge density of the electrons. So that is if you write it in a tabular form, in an equation form, it will be I equals QD into V. Okay, next. Here. Second, consider an NFET whose source and drain are connected to the ground. Okay, so source and drain, here you can see NFET, source and drain are connected to the ground. What is the charge? Now we got I. Here we got I. So we need to check now what is QD and what is V. So then we have to substitute it here. This will become I characteristics, derivation of I. Similarly, we will get it for V. Okay, so we got the general equation I equals QD into V. Now what is QD and what is V? Okay, so now second we consider an NFET whose source and drain are connected to the ground as shown in figure 2.1. Okay, what is the charge density in the inversion layer? Since we assume that onset of inversion occurs at VGS equals VTH, now we will consider VGS, that is voltage between the gate to source, is equal to VTH. The inversion charge density produced by the gate oxide capacitance is equal to VGS minus VTH. Okay, so for VGS is greater than VTH, any charge placed on the gate must be mirrored. So QD will be given by WCOX into VGS minus VTH. Very important equation this is. Now the charge density is given by W into COX. What is COX? COX is nothing but gate capacitance. Okay, capacitance oxide. Then W is nothing but the width, which is equal to VGS minus V threshold. So we got QD now. COX is multiplied by W to represent the total capacitance per unit length. So we got now QD. So further, now if suppose we take it for the pinch off region here. Okay, as you can see, this will be the pinch off region. So we will see for the pinch off region what will become QD. So QD of X, that is at the center point here, QD of X will be given by WCOX into VGS minus V of X minus VTH. So one more is added here, that is the Vx. So Vx is nothing but the channel potential at X. That's all. The potential at X here. Potential at X. So we got now QD of X and QD we got. So substituting this from 2.2, so ID will be equal to, where is ID? From 2.2, so I equals QD into V, that is I equals QD. QD is nothing but this one, WCOX into VGS minus Vx minus VTH into V. Okay, so we got now ID equation. So similarly, now again we have to simplify it, where the negative sign is inserted because the charge carriers here. Okay, Y minus is inserted here. So you can see this, there is a minus here. Y minus is inserted, minus negative sign is inserted because the charge carriers are negative, and V denotes the velocity of the electrons in the channel. For a semiconductor, V is nothing but mu into E, where mu is the mobility charge carrier and E is the electric field. Okay, so E of X is equal to minus dV by dx, and representing the mobility of the electrons by mu, we have ID equals, now substitute these things in the ID equation, WCOX into VGS minus Vx minus VTH into, that is V is nothing but mu into E, so that is mu of N, what is this is not mu of N into dV, E will be equal to minus dV by dx, so that is dV by dx. So minus minus gets cancelled and it will become plus. So this will be your total ID equation. Okay, now again subjected to boundary conditions. Now we will have a boundary condition where V of 0 is equal to 0 and V of L will be equal to VDS. So substitute V of anything, that is V of X as 0 and V of L as VDS. So what will it become? So in limiting from X is equal to 0 to L, ID into dx is equal to, again V equals 0 to VDS. So WCOX into VGS minus Vx minus VTH into this whole things becomes only dV, because V of 0, okay, that is V of X will be 0 and V of L will be VDS. So this entire thing will become dV. Now while substituting for dV here, since ID is a constant, so ID will take it out like the simplification, that's all. So that is mu n COX W by L, okay, mu n COX W by L into VGS minus VTH into VDS, because this becomes VDS minus, if you substitute here, because this dV, what happens is it will be multiplied for each thing, and even WCOX will be taken out outside. Okay, COX will be taken out outside. So when and here also, so L will be brought this side, only ID will be kept here, and dx limitation from X equal to 0 to L will be brought this side. Okay, so substituting everything, we will get mu n COX W by L into VGS minus VTH into VDS minus 1 by 2 V square ds. Okay, once substituting this, you will get this. So this is how you have to show, that is your ID versus VDS. So this is VGS 1 minus VTH, this is VGS 2 minus VTH, this is VGS 3 minus VTH. So total ID max will be given by 1 by 2 mu n COX W by L VGS minus VTH the whole square. So this one you guys have studied, you have used it in your FCMOS also. The same thing, we are just deriving it here. Okay, so as you can see this here, so ID will be equal to mu n COX W by L VGS minus VTH into VDS. Okay, so this is for saturated region, and then this will be for R on. So R on is nothing but 1 by 1 by ID. Okay, so that is 1 by mu n COX W by L VGS minus VTH. Okay, so now we'll just summarize this entire thing, how we got this, what is the derivation of IV characteristics. Now first one is consider an semiconductor bar where I is flowing inside the bar. Now I is totally dependent on the charge density Q and the velocity with which it is traveling. So I is given by QD into V. Now we need to know what is QD and what is V. So now if you take this as example, so when source and drain, when an effective or a source and drain, when both are connected to the ground, so when both are connected to the ground, what happens is VGS will be equal to VTH. Okay, the inversion charge density produced by the gate oxide capacitance will be equal to will be equal to VGS minus VTH. Okay, that is only when VGS will become greater than VTH. So it will become VGS minus VTH. Okay, so the QD will be given by, now considering this one now, where the drain is connected to VD and the source is grounded. And there will be a pinch off which will happen. So when unequal drain will be formed, unequal source and drain voltage will be formed. So if we take X as a center point, so what it happens is, for the X as a center point, so we will be substituting the charge density also. So for the first one now, QD will be given by WCOX into this one, VGS minus VTH. Now for the second one, that is for X, so then it will become QD of X is equal to WCOX into VGS minus VX minus VTH, where Vx is the channel potential at X. Okay, so now we got QD. So what will we do with QD? QD we will just go ahead and substitute in I. So I will be equal to QD into QD into V. So that is QD is minus WCOX into VGS minus Vx minus VTH into V. Now we need again what is V. So V is nothing but V is given by mu into E. Okay, so what is mu is the mobility of charge carrier and E is the electric field. So again E is given by minus dV by dx. Okay, just substitute in that particular equation. So that is COX VGS minus Vx minus VTH into V is mu, that is for micro, mu n into E is dV by dx with respect to X. So minus gets cancelled, that is become plus. Now subject to boundary condition, now there is a boundary, V of 0 is equal to 0 and V of L equal to VDS. Now limiting from X equal to 0 to L, ID into dx. Here ID into dx. So ID is a constant, we will take out ID. So for dx it will be X is equal to 0 to L. So whatever is there, we will shift it this side. So here also WCOX VGX minus Vx minus VTH into dV. So the total ID is constant along the channel. So ID will be equal to here mu n COX W by L into VGS minus VTH into this becomes VDS minus 1 by 2 V square ds after substituting. So this is your final equation which you have to write for ID. Okay, now ID for the other one is will become when VDS is very much less than, okay, so when VDS is very much less than 2 into VGS minus VTH, so we will be having ID equals mu n COX W by L VGS minus VTH into VDS. So you have used this equation earlier, so we'll just deriving it. Okay, next R on. So you R on and Q on you guys have studied in your FCMOS because of scaling, due to scaling. So R on is nothing but 1 by I, that is 1 by ID. So 1 by ID whatever is there, that is mu n COX W by L VGS minus VTH, will be adding it there into VDS, where upper VDS will be there, so VDS will get cancelled. So this is R on. So when asked about derivation of IV characteristics, you have to write all these things. Next, second order effect. You guys have already studied the second order effect in your previous FCMOS. 1 second. Okay, so we'll just brush it up now. So what are the different second order effects which are there? First is body effect, second one is channel length modulation, here channel length modulation. The third one will be sub-threshold conditions, and the fourth one is voltage limitation. So when asked about second order effect, it will be asked, you just have to write these four and explain. Okay, so we'll just brush up quickly now. Okay, first is body effect. So body effect means when n number of transistors are conducted in series. Okay, so this is gate. Okay, so these are the substrate connections which has to be connected. So if this is 0, so this substrate also has to be connected to the lower potential, that is it has to be 0. But when this is also connected here, this V threshold, that is VB, will not be equal to 0. Okay, will not be equal to 0. Similarly, when we conduct hundreds of transistors in this format, so what happens is VB, see here, VB should be equal to 0, so that will not happen. So when it does not happen, what happens is the entire device will actually fail. Okay, because the substrate connection has to be grounded and has to be 0. So but why it does not happen in that format, why it will not be 0 when connected? Because when n number of transistors are connected, so the resistance from this will also be transferred. So VB1 will not be equal to 0. VB2 also will not be equal to 0. Okay, that is what this body effect is. So this one you have to write and you have to finish. Okay, so this is the threshold equation which is there. It's the same equation, this just changes are made. So here you can see, now suppose the substrate is tied to the ground and body effect is significant, then as V in and hence V out becomes more positive. V in and V out, if we take this as example, when a transistor is connected here, V in, V out, VDD and VSS. Okay, so when the transistor is when the substrate is grounded, so this will be in parallel like this. Okay, but now suppose the substrate is tied to a ground and body effect is very much significant directly. Okay, then as V in and hence V out becomes more positive. So as we can see, V in and V out becomes more positive and it starts to move in the positive direction. Okay, and the potential difference between the source and the bulk increases, raising the value of VTH. Now when body effect increases, what happens is your threshold voltage will also be increased. So it will not be 0.7 as in regular, so it will be more than 0.7. so what happens is if you have a device which is designed in such a way that at 0.7 it has to turn on, but it will not on at 0.7 volts because of this body effect. So it might get turned on at 1.7 volts or 2.2 volts or something. So at that point of time you actually don't need your device to be turned on. So that is what will happen because of the body effect. Next, channel length modulation. Channel length is a very important characteristics when the device has to turn on. Okay, in the analysis of channel pinch off which we have studied, we noted that the actual length of the inverted channel gradually decreases as the potential difference between the gate and the drain increases. Okay, the channel length decreases when the potential difference between the gate and the drain increases. In other words, L dash, that is L effective, is in fact a function of the substrate voltage. Okay, this effect is called as channel length modulation, means you are modulating the channel depending on the length. Okay, so writing L dash equals L minus delta L, that is 1 by L dash equals 1 plus delta L by L. The whole thing will be divided by length, and assuming the first order relationship between delta L and VDS such that delta L by L equals lambda into VDS. So we have in this situation, if we put this in the ID equation, so the whole thing will become 1 by 2 mu n COX W by L VGS minus VTS the whole square plus lambda into VDS because of the channel length. Okay, because of the channel length condition. Next, sub-threshold region. What do you mean by sub-threshold region? In our analysis of MOSFET, we have assumed that the device turns off. The device, what happens here is, we have assumed that the device turns off abruptly. Okay, sub-threshold conduction. So what happens is the device actually turns off abruptly. Abruptly means immediately as VGS drops below the threshold region. But in reality, VGS will be equal to VTH even when there is no current flowing. That is, the weak inversion layer still exists, and some current will flow between the drain and the source. Even for VGS is less than VTH, ID is infinite. ID is finite, sorry. That means to say, see, what happens is, even when the voltage, we have assumed that when the voltage is below VTH, the device will stop working, right? But in reality, it will not happen so. So in reality, what happens, still there will be a leakage current which will be flowing from the drain to the source, and thus the ID will also be measured. See here, this is called a sub-threshold condition. Okay. So ID at that point of time, ideally it has to be 0, but no, it will be I naught into exponential VGS minus delta into VT. Okay, so where VT is KT by Q, and this is a non-linearity, that is, it is greater than 1, that's all. So what happens is, see, if this is the device, okay, so this is the gate, source and drain. So when gate is equal to 0, what happens is, ideally the Vout should be equal to 0, correct? So this will not happen, but Iout will not be equal to 0 because of reverse current which will be flowing from drain. Usually current will flow from source to drain, right? Because the channel will be formed from source to drain. But in this condition, sub-threshold region, what happens, due to the leakage current, the current will flow from drain to source. So when this happens, there will be a current, that is current which will be flowing in the circuit even when the input is less than VTH. So what happens by this? So sometimes you will be thinking that the current is off. So for example, you take your household switch, okay, the fan switch or light switch, because MOSFET also acts as a switch for circuits, right? So we will be thinking that it is turned off and there will be no current which will be flowing, and you put your hand in the live wire. What happens? There will still be current which will be flowing, even in the switch also, in that particular switch also. So you will get a shock. Similarly here also, if it is not turned on properly, so what happens is, the current will be flowing in the circuit which is not required. Okay, so this is why this is one of the second order effect, that is sub-threshold condition. Next, last one is the voltage limitation. So voltage limitation is nothing but MOSFET experiences various breakdown effects if their terminal voltage difference exceeds certain limits. Okay, if everything has a limit, so even this MOSFET has a limit, and if the limit reaches more than its prescribed limit, then the entire device will break. So that is the voltage limitation which the has. So this, when this happens, what happens is, when the voltage is very high, so see, this is the, consider this one, right? So this is the gate. So when the voltage is very high, what happens is, hot electron effect will happen. okay, and punch through will happen, or called as punch through. So what happens, this entire thing will be broken like this, and current will directly start flowing from gate to the channel. And when it flows from gate to the channel, whatever the conduction happens is happening here in a limited format. Both source and drain will be connected to high current. So this is what is called as hot electron effect and drain punch through. Okay, drain punch through. I'm sorry, this is not drain punch through. One second, sorry. This is the hot electron effect. Now drain punch through, what happens is source and drain. So the channel will be here, right? When there is enormous amount of power which is given between between VGS, the channel will be induced in such a way that it opens up the barrier here, as well as it punches the barrier of the drain. So there will be no closing of the channel ever. So it will be directly connected between the source and the drain. So even if you turn off the device also, the current will be flowing between the source and the drain. So that is why it is called as, that's why it has a, that's what is called as a drain punch through. Okay, next model, MOS device models. It's your last topic here, MOS device models. So these are the device models which are there. So as you can see, it is also general. So in your first unit you have to worry about your second order effect mainly, then IV derivation of IV characteristic. These two are compulsory question, internal, external, everything. So these things are all not there. Not there means not that important actually. So this one, because you have already studied all these things in your FCMOS also. So if you see that this is the circuit which will be drawn. This is MOS device layout. Okay, so the layout which will be drawn, which you have already drawn. See, these are the layouts, right? Which has the contact cards. Green is the metal, green for metal in your FCMOS. Similarly, the same thing is here also. It's just a brush up which was happening. Next, MOS device capacitance. This is one important. See, when there is a device, see this is only, this is the device. Okay, so okay, this is the device. So when this device is connected between the input and the output, okay, this is the drain, this is the source. So as you can see this in the diagram here. Okay, so when this is connected, when the device is connected in this format, there will be a number of capacitors also which will be surrounding the device. So first is between the capacitor between the gate and the source. So you can see this here. These are all parasitic capacitors. Parasitic capacitors means the capacitors which are unnecessarily formed. Okay, capacitor between the gate and the source. This is the capacitor between the substrate and the source and the substrate. This is the capacitor between the gate and the drain. This is the capacitor between the drain and the output B. Okay, output B, and this one is between the gate and the B. Okay, this is for the substrate. This is between the gate and the output B. This is between the drain and the output B. So now C1, that is, these are the capacitors. Okay, so you can see this here. In a device it will be in this format. Okay, so C1 is here, that is the capacitance between the gate region, in the gate region. C1, C2, C3, C4, C5 and C6. Now we will just see what is C1. C1 is given by WL into COX, that is width into length of the gate into the gate oxide. Then C2 is given by W into L square root of QESI N sub by 4 phi I. C3 and C4 are nothing but overlap of gate and polysilicon source and the drain areas. Okay, C5 is junction of the capacitor of source and drain area, which is given by Cj equals Cj naught by 1 plus VR by 5B into M. Okay, these all things are given here. See, everything is given here. I have just written here so that for your better understanding. Okay, so these are the capacitance which happen. So this finishes your first chapter, not first unit. So we'll go to the major chapter now, that is your analog to digital converter, that is data converter fundamentals, that is analog versus digital, and DAC. Okay, in the next class.